So today I talk about how to indirectly estimate quantum entropy via modeling
I
and
can
quantum.
hear you, and it looks good.
I see. So you can find this research in PRE. These are collaborators, Hyuk-Jung and Jae-Sung Lee. So firstly, I will talk about the difficulty of direct estimation. Let's consider Ising model and of NS spins and take data from this model. And let's say we would like to estimate it directly using this definition. Here, P bar is an inferred probability from this data. But the problem is that the state space increasing exponentially, which means we need exponentially many data to exactly estimate this entropy. And in the case of entropy production, there's the same problem. Now let's consider dynamics of Ising model. And again, we take trajectory data and estimate this stochastic entropy production from this trajectory data directly. And P bar of gamma means inferred forward trajectory probability, and P bar B means inferred time reversed trajectory probability. So again, the state space increasing exponentially. Moreover, let's say we have in the given data set, we only have the forward trajectory and there's no corresponding backward trajectory. In that case, this direct estimator diverges. So this estimation highly depends on rare events. Yeah, so to mitigate that difficulty, there are so many methods have been developed so far, like adiabatic switching method, thermodynamic uncertainty relation, or entropy bounds. And even in this WOST meeting, there have been many methods have been introduced. One of successful approaches is combining entropy inequality and a neural network. So we'll use this entropy inequality. Here, f is a function and O is an observer, which is the function of gamma trajectory. And if we can find optimal observer that can saturate this inequality, we can say that we indirectly estimate entropy production. So we use neural network to solve this problem, and we found that this shows good accuracy for, especially for dynamics with rare events. So after this research, I wondered that how can we extend this method to quantum entropy? Quantum entropy is crucial physical quantity because it is a measure of entanglement and related to some phase transition, and also can be used to estimate total entropy production under some situation. So to do that, firstly, I try to find inequality. There is an inequality named Gibbs variational principle that look like this. And what this inequality tells us is that with a given Hamiltonian H, Boltzmann state density matrix can saturate this inequality. But here, let's think conversely. This time we fixed density matrix and consider the Hamiltonian as an Hermitian observer operator. So now we'll use the left-hand side. Yeah, after some little math, we can change this Gibbs variation principle into this inequality. And we'll use this left-hand side as a cost function and solve optimal problem. Then what we find is that if the observer is given as entropy, then this inequality can be saturated. So we can use this as the cost function. But there is a still problem. This O requires 2 to the 2 ns complex numbers for spin system. And in general, off-diagonal components of dense matrix are inaccessible in experiments. So I combined quantum circuit and this neural network to sort of this parameterize this observer O. In general, Hermitian operator O can be written in terms of unitary operator V and diagonal operator D. And I used this quantum circuit to parameterize this unitary operator V. If you think about the relation between Schrödinger picture and Heisenberg picture, you can easily understand that why this unitary evolution of density matrix can corresponding to the unitary evolution of this operator D. And then what we do is that with the measurement result of this quantum circuit, we input that result into this neural network. And we'll use the output of this neural network as the elements of this diagonal operator. Okay. So in this way, we can parameterize operator O. This is the training process. These are input, density matrix, and initialize parameter sets, theta Q and theta N. And we input this information, I think, physical quantities into this quantum circuit and neural network. And using its output, we evaluate cost function. By the way, I linearize this cost function because of technical reason, but this does not change it, optimal point or optimal solution. And I applied gradient descent methods and then calculating next steps, theta Q and theta N. And I repeat this training process until the cost function saturated. Upon successful training process, we can have three outputs. The value of cost function becomes entropy, and the trained neural network can give eigenvalue, and quantum circuit can give us eigenstate. I verified this our estimator named CUNY on this XXG chain model, and while we change the magnetic field lambda, we can see that its phase transition of its ground state, and I will estimate the density von Neumann entropy of density matrix of coarse-grained ground state, so which means which is named entanglement entropy. This is the simulation result. I use 8 qubits to model this XXG chain. And for the left-hand side plot, I coarse-grained 5 qubits. So this density matrix size is of 3 qubits, and the right-hand side is 4 qubits. Y-axis represents entanglement entropy, and x-axis represents magnetic fields. And orange dot is the result of our estimator CUNY, and blue symbols represents baseline model, so-called VQSE, and black line is the exact value of entanglement entropy. So you can see that near the boundary between the massless phase and ferromagnetic phase, we can see CUNY can accurately estimate entanglement entropy. This result suggests that we can use CUNY as a phase classifier. And these are the other output eigenvalue. And you can see that for phases, CUNY and VQSE shows comparable estimation accuracy. Actually, the baseline model VQSE is specialized for estimating eigenvalues. CUNY is also good for estimating eigenvalue. And the bottom plot represents training curve, and this suggests that around 100 iteration is enough to classify this massless phase and ferromagnetic phase. Okay, this is summary. By combining neural network and quantum circuit, quantum entropies can be estimated, and CUNY can classify phases even with less resources. And I would like to emphasize that the way this idea to combining neural network and quantum circuit has a broad applicability. So in the paper, you can see how to estimate Renyi entropy indirectly. So here is the advertisement. I hope to work, and please let me know if there is a postdoc opportunity. So thank you.